Okay, for those of just those who are joining us from the recording, we're going to talk today about circuits. So this one is going to be practice quiz 2-1 at the very bottom under files if you want to follow along. I'm also going to share screen. Oh, no, I already am. Look at that. All right, cool. So again, this is more in the style of a midterm question or a final question than a practice quiz. However, the concepts will still carry over. So let's get started. And again, if y'all have questions, feel free to just type in the chat or just verbally interrupt. No big deal. I'm going to pull the chat over so I make sure it's right in my field of view. Okay, so we've got a circuit. There's a battery. This is how we mark a battery. We've got 3 resistors, 3 ohm resistor, a 2 ohm resistor, and another 2 ohm resistor. And I've got a bunch of wires linking everything together. So A asks me, for the circuit shown here, calculate the current I coming out of the battery. Quick chat coming in. Okay, I think y'all got it. Calculate the current coming out of the battery. Explain your answer. Okay, so I actually want to break this into 2 parts. I'm going to do a little bit of extra work. So I'm going to do some extra work over here. Let's say I want to imagine a slightly different circuit. This is not strictly this quiz, but let's imagine a slightly different circuit. 12 volts on a battery, a 3 ohm resistor, a 2 ohm resistor, an upper branch that has 2 ohms, boom, something like that. Here's A and B again. This one's also 2 ohms. Okay, so same question though. If I want to think about the current coming out of this battery, let's think about where it can go. So current flows out of the positive side of the battery, goes through the resistor. Here's my current flowing up. It hits this junction. It can go either this way or this way. So there's a junction here. It comes up, it goes through that resistor. If it doesn't, it goes through this resistor. So I can think about these resistors in their relationships to one another. For example, these 2 resistors up here are in parallel. Their tails, their sides that are taking in the current are connected to one another. So these 2 are in parallel. I would say also that this resistor here is in series with the other 2. So the things that exit its head enter the tails of the other 2. Does that make sense? I'm using this kind of like head tail like verbiage. So what I mean by heads and tails is that the current that is leaving the lower resistor is entering on the how do you say this? On the side that takes current for the other 2 resistors. So like these 2 resistors, I can see just kind of like tracking where the current must flow to reach the tail side. I can see that the current flows into the right side of these upper resistors. So the right side of the upper resistors are their tails, and the right side of the lower resistor is its head. That's where current is exiting from. Hopefully that's all right. That's what I mean by heads and tails. Tails are the side that take the current in, heads are the side that let the current out. Okay, all right, so were my original quiz question just like this circuit without this wire, this lower wire, then I could just use I could just reduce this circuit to a circuit of equivalent resistance. What does that mean? It means I would take these resistors and try to reduce them to a single resistor. And that would be my problem. However, because I've got this lower wire here, I have to think a little bit more carefully about this circuit. So this circuit isn't just like, you know, a resistor and then 2 resistors in parallel. It's a resistor and then a short. So what a short means is a section of wire that cuts off another part of the circuit. So let's just look at this resistance-wise. So first things first, I cross over my resistor. I'm going to lose some voltage to that resistor. Okay? Now, after I've lost some voltage to that resistor, here's my current going through. I come out on the other side, and if I imagine myself now as a little charge here, a little positive charge, I have a couple of options. I can go up to where there are resistors I have to pass through, or I can go down where there are no resistors I have to pass through, and I can cleanly go back to the tail of my battery, the negative end of my battery. So what am I going to do as the charge? I'm pretty much always going to choose to go the easy way. I'm going to go the easy way, that is avoiding all of these resistors. So let me real quick erase a few things and then lock something. Let me lock this. Here we go. So if I'm looking to find the current exiting my battery here, there are a few ways I can do that. They're all going to involve Kirchhoff's voltage law, Kirchhoff's loop rule. So I can think of a couple of loops. Okay, let's think of a couple of loops. I'll start at the tail of the battery and I'll end at the tail of the battery. Initial, final. So there are 1, 2, 3, 4. I think there are 4 loops that I can draw, maybe 5. I'm only going to concern myself with loops that involve the battery. So here's a couple of loops. Here's loop 1. Here's another loop. And here's another loop. Each of these start at the tail of the battery and end at the tail of the battery. I've got a question coming in. Wouldn't the top 2 resistors be receiving the current, and therefore that would be the head, not tail? So the way that I think of it is that the tail of the resistor, the way that I think of it is that the tail of the resistor is the one that's receiving current, and the head is the one that's spitting it out. Yeah, but it's kind of up to you. If you prefer to think of it the other way, that's okay. But the image that I want to have is that, like, if 2 sides that are both receiving current are connected like this by a wire, then these 2 resistors are in parallel. If one side is spitting out current and then the next resistor is receiving current, I would call that in series. Okay, how are we doing? Can I get thumbs up, thumbs down? Claps if you're having an okay time. Ta-das, or the little party poppers if you're having a bad time. Oh no. Okay. Okay. Well, please, I'm welcoming questions. Questions always. Okay. So what is Kirchhoff's? Yeah, go for it.
So when you were talking about how obviously it's going to take the easier path, that's just because like nature is not going to think, oh, let me just do this harder thing. Like, no, because naturally it's going to use whatever is going to take the least amount of energy, right?
Right. That's basically the way that I think of it from a physical perspective, is that the charges will take whatever costs them the least, whatever they have to spend the least energy to go through. Yeah. So yeah, there's a little bit of nuance to that, because like if things only ever took exactly the path of the least resistance in the sense of least resistors, then like if I had this lower one be 3 ohms and this upper one be 5 ohms, then like none of it would go in the upper one and it would all go in the 2 ohm one. So it's slightly more complicated than literally all of the current taking the path of least resistance. But it will split out. Current will split at this junction according to the relative difficulties of going through each of these upper and lower resistors. So like if this one was 5 ohms again, and this one down here was 2 ohms, if current, so let's again cut off our short. Let's pretend the short's not here. So current would flow through this 3 ohm resistor, move up to point B, and then we'd have a decision. Should I go down the 2 ohm path or the 5 ohm path? And more current, more charges are going to choose to go down the 2 ohm path. Some of it will still go up the 5 ohm path, which we can write out why that is. Maybe if we want to come back and talk about this simplified circuit over here. But for now, since I started on the Kirchhoff's loop rule path, let's show what Kirchhoff's loop rule is in the context of some of these loops. So let's say this is loop 1. Go ahead. This is loop 2 and this is loop 3. Question?
So the one at the top is actually 5 ohms, not 2 ohms?
The one at the top is actually 2 ohms. I meant to talk about it in the context of this one having more resistance than this one, to say, give some intuition for how current splits. Namely, it tends to choose the path of lower resistance, but some of it might still go down the path of greater resistance. And we have some math for that. Linda asks, I think I missed it, but what does the omega stand for? Omega stands for ohm. It's just a measure of resistance. So some intuition for resistance is that resistance is a measure of how much energy a charge has to expend to go through a region of a circuit. So a resistor is like something that takes energy for my circuit to go through. I think of it sometimes like a light bulb. A lot of times it's something that does meaningful work. A true resistor is just something that dissipates energy as heat. So it's kind of like a little heating coil. Okay, let's hit Kirchhoff's loop rule here. So what does Kirchhoff's loop rule says? It tells me that the changes in voltage, the sum of changes around a circuit, around a loop, equals 0. Or in the lecture notes we see this as, or in the DL manual we see this as delta V loop equals 0. All of the changes in voltage around a loop sum to 0. So notably, let me first apply that to loop 1. So here it is for loop 1. This lower loop. So what that tells me is, let's start at this initial point. As I flow with the current, first I encounter the battery. That tells me that delta V battery is going to be in the equation. So I'm just applying this equation over here. So the next thing I encounter as I traverse around this loop is this resistor. So plus delta V resistor 1, I'll call it. And then as I continue around this loop, all I hit is a bunch of wire. So that doesn't contribute to my voltage changes. There is no change in voltage between 2 points connected by a wire. That's your general statement. There's no difference in voltage between 2 points connected by a wire, because the wires are resistance free. So they don't sap any energy by current traveling between 2 points connected by a wire. Okay. So delta VB plus delta VR1 equals 0. In terms of our equations, the change in voltage across the battery as I flow from the tail to the head, or from the left side of the battery to the right side of the battery here, is 12 volts, which means that the change in voltage across the resistor must be negative 12 volts. So delta V resistor 1 equals minus 12 volts. Okay, so sweet. The change in voltage across resistor 1 is minus 12 volts. Now, conveniently, if I'm trying to answer the question of how much current is exiting the battery, this loop gives me all the information I need to do that, because all of the current exiting the battery is going into the resistor, this resistor 1 here at the bottom, who I've just calculated a 12 volt voltage change for. So the reason that that gives me current is because of another law called Ohm's law, which says basically that the voltage drop across a resistor is negative current magnitude times the resistance of that resistor. Basically what this tells me from a fluids perspective is that the faster a current is flowing through a resistor, the more energy is dissipated. So if you want, you can imagine if I had a rough pipe in the fluid setting and I threw a bunch of current down it, more of that current per unit's time is going to be crashing into the walls of that rough pipe and dissipating energy. So yeah, so what this tells me is that as I increase my current, my change in voltage also increases. I dissipate more energy. Is that okay for now? Questions while we're here? Okay, so just to kind of finish this one out, and oh, sorry, that was a question. Jordan.
So it's more current equals more voltage loss?
That's right. More current means more voltage loss for a given resistor. So more current will usually also mean a larger starting voltage. So like if I attach a 9-volt battery to a resistor, I'm going to get more current out of a single resistor than I would for a 1-volt battery attached to that same resistor. Yes, I try to relate this again over to pressure. So voltage roughly corresponds to pressure. So if I have a very low fluid flow system, like a low rate of fluid flow system, and I consider a rusty pipe, because there's not that much energy to begin with for that pipe to pull energy from, the pressure drop will not be that significant. So if I've got a slow moving fluid in a rusty pipe, the pipe can only pull out a little bit of energy anyhow. It's only seeing a little bit of current pass through. Okay, hopefully that works for intuition building. At the end of the day, this is our expression. Ohm's law, the change in voltage across the resistor is negative current magnitude times resistor magnitude. Okay, so in our context, what does this tell me? Well, we've just found that the current through this resistor, which is the one directly pulling current from the battery, all of the current exiting the battery is entering this resistor, is negative 12 volts. That's negative I, whatever the current is, times that resistor magnitude, which is 3 ohms. Okay, so then I can just solve this back. I get a current of 4 amps. Are we going to be given a formula sheet during exams? Yes, we will have. There will be a formula sheet appended to the back of the midterm and the final. That's the question. Okay. So that's it for for A. So what did I do? I looked at a bunch of possible loops. I used the loop that to me looked simplest, and that happened to work out. So what did I do? I used the lower loop. And I said, okay, change in voltage around this loop must equal 0, which means that all of the battery voltage is absorbed by this first resistor. The battery voltage being absorbed by this first resistor means that I could use Ohm's law to determine the current flowing out of the battery. All of the current entering this resistor was the current exiting this battery. So I could use Ohm's law to find the size of that current.
Just a quick question. That's supposed to be negative 12 volts equals negative current times 3A.
3 ohms. Yeah, 3 little omegas. Negative current times times 3 ohms. So the 3 ohms here is the resistance of our resistor.
Is
So
that
Thanks, Jordan.
an R?
Say again?
Is that a 12 or an R? Next to that.
This thing over here? Yeah, this
Yeah.
is 12. Yep.
Okay.
Yeah, and I know my handwriting's not that great, so no worries.
Thank you.
This is just to say that the change in voltage across the resistor is negative 12 volts. So I'm pulling that from over here. There we go.
So if we didn't have that lower loop and we were just looking and they had equal current, how would you be picking one, or how would you solve it in that case if they had both the same resistance value?
Yeah, sure. So these ones here, like
Yes.
say that I didn't have my short. So if I didn't have my so when I say short, I'm referring to this lower thing here. Short just means that I'm like cutting off a section of my circuit. Recall that anytime I connect 2 points by a wire, their change in voltage must be 0, which means that in this case, like if I put this little orange wire in this simplified circuit, then each of these resistors must also have no voltage change between them because they can be connected by a wire this way. Okay, but so to come back to the question, if it were the case that I had only these upper loops, so I'll draw them in pink, loop 1 here and loop 2 here. If I had these upper loops, then in order to calculate the battery voltage, I would actually need 3 terms. So if I use this lower loop, I would say delta V battery. Okay, then I encounter my first resistor plus delta V R1 I'll call the lower one R1. Let's go ahead and label the resistors just so we know what we're talking about. This is R1, this is R2, this is R3. 3. Okay, so if I were to use this lower loop, I first encounter the battery, check. Then I encounter the first resistor, check. Then I encounter this 2 ohm resistor, R2, plus delta V R2. And then boom, I get back around to the beginning of my loop, the tail of the battery, equals 0. Okay, so substituting some things in, I've got the battery voltage, that's 12 volts, plus, so the first resistor is taking in the battery voltage, I should say minus here, minus I battery times resistor 1's value, which is 3 ohms, plus, okay, now, delta V of R2 is a little bit more complicated because instead of it being just the battery voltage that would be entering this R2, or the battery current that's entering this R2, the current that is leaving the battery entering this R2, the current exiting the battery has to split into 2 parts. So I battery up here, and then I'll call it I2 and I3. So I3 or I2, the current entering this 2 ohm resistor is going to be smaller than the current exiting the battery. And because these 2 resistors are the same size, it turns out that they're going to be the same size, I2 equals I3. However, it's not immediately clear why that would be. So I'll come back to this one at the end if there's time, and we'll solve this simplified circuit because it takes a little bit more math and a little less intuition. But there is a way that you can do this kind of circuit in general too, by circuit reduction. So by reducing these upper, what do you call these? These upper things to a single resistor, and then calculating the changes in voltage across all of them, and then coming back and using Ohm's law on each of these upper ones. But again, that takes a little bit more time. So I will come back and do that if there's time at the end. Sound good? Okay, there's another question. If we calculated using the above path, would we get a different value? That's related to this question. What I'll say is that as is, if you tried to calculate using the above path, if you tried to use the above path alone, you would find that the current through these upper ones would be 0. So you would end up eventually with the same, value, but it would take a little bit more of a convoluted path. And again, I think that'll be made clear at the end if we talk about this.
One more question on this. How come, if we're taking the lower paths, how come we don't face like the same split in current that we would if we only had like the 2 upper paths?
So we do, if we, not knowing anything about our lower path, we can conceptualize of a splitting in current. So if this is I battery, I can think of it as an I upper that goes up and an I lower that goes down. However, in completing this first loop, we never actually need to use I lower because there are no circuit elements on this lower part of this branch. There's only the stuff that is, there are only batteries and resistors that are on the same little path here that are taking the battery current, all the current exiting the battery. So if there were to be a resistor down here, then we would need to think about that current splitting. We would need to think about that it's a different value. However, because all of the current that is exiting the battery enters all of the elements on this lower path, so like all of the current exiting the battery enter this first resistor, and then there's nothing to even consider on this low section down here, we don't actually need to do the math of calculating I low and I up. Does that help? So it's basically because as I traverse this loop, I don't encounter anything beyond the split.
Okay, I think I get it now. Thank you.
Okay, yeah, sure. Okay, B, for the same circuit, find the voltage difference between the points marked A and B. Explain your answer. I'm gonna go ahead and clean this up a little bit. It's getting a little bit messy. So there we go. Okay. So it asked me to find the voltage difference between points marked A and B and explain my answer. Okay, so the tempting thing to do the tempting thing, if you only knew the equations, would be to say, okay, well, I've got some current that I know is flowing through the system, I, and maybe it's flowing through up here as well. So I can use IR and find that the voltage difference is just delta V equals IR. Battery voltage times, or battery current times the resistor. But that's a path that you should be careful of. So here's why. Number one, we do have these splits. So like splitting of current, we have multiple junctions. So we can't just use the battery current up here. We can't just use the battery current up here because the battery current, the only thing that we know it's flowing through, like directly flowing through, is this 3 ohm resistor down here. After that, there's a bunch of points where it could split. So the full current certainly won't be traveling through this 2 ohm resistor. There's actually another level of meme here. It's a little bit deeper than that, which is to say that the points A and B are connected by our short. So the verbal principle again is 2 points connected by a wire must always be at the same voltage. So 2 points connected by a wire must always be at the same voltage because the wire is resistanceless. So if I just took a path from point A to point B, there's nothing in the way. Like there's nothing in the way between those two. I can find a path where there's nothing in the way between those two. So delta V between A and B is just 0 because they are connected by a wire. Okay, so the implications of this are like pretty significant. Notably, if the current or if the voltage difference between A and B is 0, if VA equals VB, the current at A or the voltage at A is equal to the voltage at B. There we go. If the voltage at A is equal to the voltage at B, there we go. All right. Then that tells me that the change in voltage across this resistor is 0, which by itself doesn't necessarily tell me that much about how the charge is flowing. But when I look at Ohm's law, delta V equals negative IR, what that tells me is that this short, this wire here, made it so that no current at all is flowing through this upper resistor. Similar logic applies for this upper branch. So the change in voltage here is also 0. Because, well, this point and this point are also connected by a wire. So their change in voltage is 0, which means that the current through both of these upper branches is actually 0. All of the current is sapped by this short wire. All of the current goes through this region of 0 resistance. Yeah, so that's why shorts are bad, if you like, is because if you were operating your computer or whatever with these upper resistors, if you had some load up here that you wanted to have operate, and then you accidentally connected a wire in the wrong place, you just totally remove all of the energy from the parts that you wanted to give energy to. Also, when you short something, you skip out on some resistance. So the current will tend to be larger than you anticipated, and that can be bad too. That could like overload this resistor, for example. Okay, that's kind of an aside though, just to try to help build a little intuition. Okay, let's look. I've got a couple of more questions, but that wire has a resistor. Does that change the current? So I think is the question, this section of wire has a resistor. Does that change the current? Is that what it is?
I was asking because we were talking about the top one with the 2 omega, and that one has a resistor between those 2 points. Would that change the voltage?
Good. So still no. So the underlying principle is still that two points connected by a wire must have 0 voltage change. So what so I could take 2 paths. So let's take 2 different paths. So say that I took the path directly across the resistor. What that path would show me is that the change in voltage between A and B, so let's say I took this path to A, took this path from B. The total voltage from A to B is negative I'll call it I3, the current flowing through this third resistor here, times R3. So that's still true. However, if I take this other path, so we'll take this path, I'll mark it in blue instead because I'm getting too many colors in here, or green, what I say. Okay, if I mark it this way instead, so if I take this path following the wire, what that tells me is that delta V AB equals 0. Both of these statements must be true because all I did was follow a path. Both of these statements must be true. So in order for both statements to be true, because R is a positive number, and because VAB must be 0, I3 must be 0. Does that help? So I can approach it either way, or I kind of need to approach it both ways. So when I approach the path from B to A by crossing over a resistor, I get that the change in voltage from B to A must be negative the current passing through that resistor times the resistance of that resistor. If I take this alternate path around this wire, I find that there must be no change in voltage because I didn't run into anything. Both statements must be true. So that tells me that the current passing through the upper resistors is 0.
That helps. Thank you.
Yeah, good.
So you essentially need to explore all of the paths in order to determine these things.
So exploring all of the paths eventually gets to be like a large problem, right? Like if I explored all possible paths, I'd have to go through 4 paths. But I would say take a look. Some paths are going to be markedly different from others, probably visually. Like here, this lower section being just a wire, for me that raises a flag. I'm like, wait a minute. You know, I'm used, like usually there are circuit elements on things. When there aren't circuit elements on a section of wire, that tells me that something might be going on there. Like, yeah. So the paths that you choose, usually if you just use one path, like say you use a given path, and then you realize, oh wait, I don't have enough variables to understand the problem or to complete the problem. Like I don't have enough knowns to complete the problem. That's when it's a good idea to branch out and say, okay, I need another answer. I need another path. So like if I had just taken the upper path, taking the upper path alone doesn't tell me anything about I3. So I don't get to know what the change in voltage is just by taking the upper path. I have to think about other paths as well. And the path that happened to help me out there is the one that follows the short, that follows the wire. It tells me that the change in voltage is 0. Okay, we got about, yeah, go for it. Question.
For that top, for number 1A, so you know how you said that if you connect 2 points with a wire, the change is 0. So why isn't the change 0 for the change in voltage of the resistor?
So of this resistor here?
Yeah.
Okay, cool. So the 2 points on opposite sides of this resistor, I'm gonna go ahead and erase some of this stuff again. There we go. Okay. So these 2 points across this resistor, the change in voltage there is non-zero because these 2 points are not connected by a wire. So it is true that the change in voltage between, I'll mark them in pink, between these 2 points is 0. So these 2 points, I'll call this one A prime and B prime. Delta V, A prime and V prime is still 0, B prime. Does that answer the question or not quite? So I can show also why the change in voltage here is non-zero if you want.
I'm assuming it's because the short is connecting A to B, but I to F, or yeah, I to F is just too short, or like it's like literally like not long enough, right?
The thing is that these 2 points, so in order for these two points to be at the same voltage, I would need for a wire to connect them directly, like that. So when I say a wire connecting them directly, the reason that this point and this point are not directly connected by a wire is because there's a battery in the way. So say that I look at my short, right? I follow my short around and boom, there's a battery there. So this point I guess we'll say, this point here in between the battery and the resistor is not directly connected to the opposite side of that same resistor. It's not shorted. An example of what would be shorted is if I had a wire that went around like this. Boom. So that's shorted. Now, if I had a wire connecting these 2 points, the change in voltage across this resistor would be 0.
Okay, thank you.
Does that help? Yeah, sure. Thanks for the question. Another question, charges, to clarify, charges won't travel through a resistor unless they have to. So roughly, yes, that's true. So if they have the option to go down a wire, they'll always choose the wire. I can demonstrate that a little bit and draw that over to parallel resistance. So say that I had a battery like this that has a resistor, and then I have a resistor up here and a wire down here. Okay, so if I were going to do conventional circuit reduction on this, what I would try to do is reduce all of these resistors to a single resistor. Here's R1, here's R2, and this lower section down here, I'll call it like a phantom resistor. There's nothing actually down here. I'll say R3 equals 0. So this branch allows for current to run in either direction, up or down. And if I look at the equivalent resistance of this resistor, so this quote resistor, I can add these 2 resistors in parallel, 1 over R2 plus 1 over R3. Inverted is R equivalent. But wait, R3 is 0. So if R3 is 0, then this is like infinity inverted, which is like 1 over infinity, which is like 0. So which is to say that this section of wire makes it so that the current basically only sees that lower section. It makes it so that it will only travel through the region where there's no resistance. Hopefully that makes some sense. So yeah, okay, cool. So again, this little example, it might be more confusing than it's worth. What I'm trying to show is just that the equivalent resistance of a region that is shorted by a wire is 0. It's just the resistance of the wire, essentially. So all current will choose the wire if they have the option to choose a 0 resistance path. Okay, let's hit the last section here. Got about 5 minutes left. We will see if there's time to head over to this one and do a more complicated circuit reduction. I'm given a battery, 2 5-ohm light bulbs, and 1 10-ohm light bulb. Build a circuit using the battery and the 3 light bulbs such that the 2 5-ohm light bulbs have equal brightness and the 10-ohm light bulb is dimmer than the 2 5-ohm ones. Hint, brightness is determined by power dissipated in the light bulb. Draw the circuit and explain your answer. So they give me a hint about power. So let's include an equation for power. Power is current through an element, through a circuit element, times change in voltage across that element. So if I have
That's a quick question.
Yeah, go for it.
Sorry. Can't we just assume that the 10-ohm light bulb is going to be dimmer anyway because it's already using up more energy than the 2 5-ohm light bulbs? Or is
So
that like
it depends.
hella wrong?
No, it's not. I mean, it's more just like it depends on the circumstance. So like I can have different currents in different parts of my circuit. So for example, okay, check this out. Yeah, this will make sense. Okay, so for example, I can make it so that the 10-ohm light bulb is actually, I think, brighter than the other 2. I'll design a circuit like that real quick. So let's say that I change myself up. Let's show a circuit which has the 10 ohms bulb as brighter than the others, just to show that we can have that option. So there's a few ways to do that. One way is to just have a battery that connects to all 3. So straight up like this. So here's the 10 ohm, here's the 5 ohm, here's the 5 ohm. Let's bring it back over. So each of these resistors shares the same current. The I battery current travels through each of them. So in that case, each of them will just have power dissipated by, by the amount given by I battery. So delta V equals IR. So we can also write this as I squared R. There we go. So in that case, the 10 ohm bulb would be twice as bright as the other two, because the power it dissipates is IB squared times 10, whereas the other should dissipate IB squared times 5, IB squared times 5. However, I don't have to arrange it this way. I could instead arrange it so that my battery hits, I don't know, let's say something like this. Let's say it hits, let's say it hits the, let's make a branch. This will be fun. Okay, so let's make a branch into the upper region for 5 ohms. And then we'll make another branch, 5 ohms. And then what do we want to do next? Let's say that I put my, I think there's a simpler way to do this. Let's do it like this. Okay, check this out. Let's say that instead I design it so that they're all in parallel. So I put them all in parallel. I'll put my 10 ohms up here, my 5 ohms down here, and my 5 ohms down here. So if I design the circuit this way, oops, 10 ohm. All right, now, now we're talking something a little bit more. Now we're talking something a little bit more interesting, I think. So the change in voltage across each of these, is going to be the same. So let's draw a couple paths, and I'll explain why that is. So if I've got a battery voltage epsilon, and I follow it around, boom, here's one path. Here's another path. And here's another path. The current in each of these bulbs is no longer the same. Or rather, like the two 5 ohm resistors still have the same current through them, but the 10 ohm one is going to have a different amount of current. The current from the battery splits into 3 parts. I'll call it I1, I2, and I3. So they no longer dissipate the same power in general. So let me rewrite this one more time. So we can also write this as delta V squared over R. Double check myself on that. So I substitute the I in. Yeah, that makes sense. Okay, so that's another expression for power. I just used Ohm's law to substitute in. So each of these resistors following each of these paths has to dissipate the battery voltage. So let's follow the blue path first, for example. I start here, I go across the battery, I get a battery voltage. Then I flow up the resistor, I get a minus delta V resistor 1 equals 0. The red path, I get the same. Battery voltage minus the change in voltage across that that resistor 2 equals 0. This is 1, 2, 3. And finally, for the last one, battery voltage minus delta V R3 equals 0. So this tells me that each of the resistors now dissipates the same voltage. The power dissipated by each of them, that corresponds to the brightness, is now going to be larger for the 5 ohm bulbs. Why? Because power is change in voltage squared across that circuit element divided by its resistance. So things which have lower resistance in parallel actually dissipate more power. So this is an example of a circuit which has brighter 2 bright 5 ohm bulbs and 1 dim 10 ohm bulbs. Connecting things in parallel makes it so that things have the same voltage drop across them. So like if here's point A, point B. the voltage difference across A and B is the same regardless of which path I take. So yeah, so delta VAB is the same regardless of which path I take, whether I go across the 5 ohm resistor or the lower 5 ohm resistor and so on. Okay, so this is an appropriate circuit here. Yeah, quick question.
Quick question. So why do you subtract the delta VR1 or like?
You're right.
Voltage?
I should make these positive. So in my head, I just know that the changes in voltage will be negative. So I kind of had a little like mental slip there. So
so how did you know that also then?
Yeah, sure. So resistors always take away voltage. So resistors are sinks for energy. They absorb energy density from the voltage and turn it into heat. That's what they usually do, is just cause a heat up. So anytime I pass through a resistor, it's like passing through a section of rusty pipe. It's like passing through an area that takes energy away. So since this loop law carries with it like a notion of energy conservation, it's saying that if I go from one point and return to that same point, the voltage must be the same. The energy per charge must be the same. I know that anytime I pass from the tail to the head of a battery, I get an increase in voltage. And anytime I flow along a resistor in the direction of the current, it's going to take away energy.
Oh,
does that help?
Yeah. So basically, if you follow the resistor like along the path that you would expect it's going to like take away energy.
That's right. If I follow the resistor along the same direction that the current is flowing, it's going to take away energy.
Okay, sounds good. Thank you.
Yeah, sure thing. Okay, so just to clarify, the voltage taken in by the resistor is all the same, but the power is different for each. That's right. Each resistor has the same voltage drop across it, but the power is different because of the different resistance amount. Okay, thanks everybody. I know we're a little bit over time. I'll stick around for like 2 or 3 more minutes to take questions, but otherwise, I think I'll go ahead and end the recording here. Thanks for hanging out. And yeah, I'll see you next time.
Thank you.
Sure.
Hi, Professor. I had a question about like logistics.
Yeah.
I have to drop 7B now, but I registered for that other course, the Physics 49.
Okay.
I think it's gonna mess with the Canvas, like my Canvas access. So if I drop it today, should I send you?
Yeah, please do. If it does drop you out of Canvas, just let me know and I can add you back in manually.
Okay, sounds good. Thank you.
Cool. I'll look out for it. Thanks, Paula. Jeffrey asks, sorry, I always shorten names, so I probably shouldn't. Jeffrey asks, how do you know that the voltage change is the same for A and B if there's no free wire that connects them? Okay, good. So I'm not saying that the change in voltage from A to B is 0. It's not equal to 0. I'm just saying that regardless of my path that I take from A to B, whether I go through the upper resistor or the middle resistor or the lower resistor, the changes in voltage are the same throughout, which is to say that delta V R1 from here to here is the same as delta V R2 from here to here, which is the same as delta V R3 from here to here. I'm not saying that the change in voltage is 0. Sorry about that.
Oh, and then is what allows you to say that is because of Kirchhoff's loop rule? Is that why you said all of them equal?
So strictly speaking, Kirchhoff's loop rule just tells me that around a loop, the change in voltage equals 0. So like if I included the battery and went around through any of these, it equals 0. So I'm appealing to a little bit more general of a principle, I guess, which is that regardless of the path that I take between 2 points, the change in voltage will always be the same. So voltage can't have multiple different values based on which path I choose to get there. It's equivalent to Kirchhoff's voltage law, but it's a little bit more general, and I think it's more useful. So like, okay, so like, let me think of another little quick example. So Okay, so say I had a battery like this, and I told you that, okay, and I told you that the change in voltage across this resistor, delta V across this resistor is 2 volts. And I also told you that the current flowing through this region, now I want to tell you about the current. So if I told you that the change in voltage across this region was 2 volts, and then I asked you to find the change in voltage from here to here, what's that delta V? The temptation is to, I mean, I think that the dangerous temptation is to say, okay, well, I need to find the battery voltage, and then I'll find this current, and then I'll find that current, I'll find this current. And after I find all those currents, I can say what this delta V is, add that to this delta V, and I'll get this delta V, right? So, so the point is that's complicated. And there's a simpler notion that we can appeal to, which is basically that regardless of how I get from one side to the other of this little junction here, the change in voltage must be the same. So I already know this change in voltage is 2 volts. So I know that the total change in voltage, regardless of path that I take here, is also 2 volts.
Oh, so it's just more of like a continuity thing instead?
That's right. That's how I think of it. It's kind of like an extension of continuity.
Okay.
It's not so much about, so if I was going to be like super precise, I would say the continuity equation most cleanly maps onto the junction rule, which is that current exiting a junction must be the same as the current entering a junction, but it's the same kind of concept of conservation. Yeah. If you're comfortable with it, I'm comfortable with it. But that said, the way to think about it for me is like, if I were to find that the change in voltage here was like a different number, like 1.5 volts, then say that I started over here and I called this side, it's at 3 volts. So if I take the upper route, I would find that the voltage at this point is 4.5 volts. And if I took the lower route, I'd find the region at this point is 5 volts. But wait a minute, these two regions are connected by a wire. So they're not supposed to have any voltage difference between them. So I've got some kind of like contradiction there. So the statement that two regions connected by a wire must have no voltage difference leads cleanly to this notion that regardless of the path that I take between 2 points, the voltage difference must be the same.
Okay.
Yeah.
All right. Thank you.
Yeah. Thanks, Jeffrey. And if that doesn't make sense just yet, give it a minute, stew on it a little bit, and I'm sure you'll encounter it again in more problems. Okay. I think that's it for now. We got one more. Oh, you're welcome, everybody. Okay. And I'm going to go ahead and cut off the recording here, and we'll see you next time. Thanks, folks.